So part 2 of this video is going to continue talking about special functions. And now we're going to talk about a constant function. And constant functions mean there's no change. So these are going to be, for example, a horizontal line. There's no change over time. If you see f of x equals -3, you really should be thinking to yourself, y equals -3. Where is y equal -3 all of the time? No matter where I go, 2, -3, 0, -3, -4, -3. I'm talking about a horizontal line right there. And that is what a constant function is. It doesn't have any change. So it's really just a flat growth. When you think about functions and relationships, nothing changes. So if you have to pay a flat fee no matter what, that's a constant function. The identity function is when what you put in, you get out. So if you think about this as being y equals x, whatever x is, y is. So 0, 0. If x is 1, y is 1. If x is 3, y is 3. If x is -3, y is -3. And so we get this steady one-to-one constant rate of growth. When we're talking about this, our domain is all real numbers, and our range is all real numbers. And if I go back just for a minute on this constant function, when you think about the domain, what you can put into this for x values is really all reals. I can put anything I want in. For the range, what comes out is y equals -3. No matter what I put in, the only value that will come out is y equals -3. Now, piecewise functions are functions that have two different or more behaviors. So they behave differently over different intervals, kind of like ceiling and floor functions. When you think about an absolute value graph, your two pieces are really, if you think about this as your y equals the absolute value of x for a minute, remember we know x can be positive or negative. So when y, we know that this really is that a matter of x could equal -y or x equals y. We know that it has those two behaviors, and where that changed is when x is negative versus positive. So when we were finding these, it caused different values. So what happens in a piecewise function like this is I know if I put, and this is another way to think about it, if I put -3 in, I'm going to get +3 out. If I put 3 in, I'm getting 3 out. If I put -2 in, I get 2 out. 2 in, I get 2 out. And at 0, I get 0. Absolute value graphs are always going to make a V shape. They're not curved like a parabola. They are a very strict V. So at -3, it was 3. At -2, it's 2. At +2, it's 2. At 3, it's 3. And so what happens is for x is less than 0, my graph behaves one way here. And for x is greater than 0, here my graph behaves in an entirely different way. So that is one example of a piecewise function. Here is another great one, and it flat out tells me where my x behaves differently. And so for values, it's like using two different set of directions. For x is less than 0, if I put x in, I'm going to get -x out. So when x is 1, I get -1. When x is -1, I get +1. When x is 0, I get 0. When x is 2, I get -2. And so for positive, oops, x, wrong values, I can't, x is less than 0. I can't put that in there, and I can't put that in there. So what I should have put in there was when x is negative 2, I get 2 out. When x is negative 3, I get positive 3 out. So at 0, 0, at negative 3, positive 3, at negative 1, positive 1, negative 2, positive 2. And you'll see this is just another way when x's are greater than or equal to 0, and here's where I can use my 1. My graph is going to say x. For x in, I get x out. For 2 in, I get 2 out. For 0 in, I get 0 out. And this piecewise function here, when you compare, is exactly the same. So the way these two act are exactly the same. Now let's look at the absolute value here of negative 3. So let's start putting, we have no restrictions. This is going to be a V-shaped. We have to find the bottom of the V-shape. So x I put in, I'm going to get x minus 3 absolute value out. So if I put 0 in, I get 0 minus 3, which is negative 3, which is 3. If I put negative 1 in, I get negative 1 minus 3, which is negative 4, which is positive 4 out. And I'm going to keep on trying values until I see a pattern emerge. So what if I put 3 in? I get 3 minus 3, which is 0, which is 0. What if I put 4 in? I get 4 minus 1, which is 3. And the absolute value of, whoops, I did that wrong. I get 4 minus 3, which is 1. And I see that I've switched from 0, and now my answers are going back up again. And so I can go over here and start to graph this and see if I'm getting my V shape. So when x is 0, y is 3. When x is negative 1, y was 4. When x was positive 3, y was 0. When x is 4, it was 1. And indeed, I am starting to get that V shape. And so that is what that absolute value graph is going to look like. When I talk about the domain and the range here, the domain, what can go into this function? Everything. All reals can go in. What's going to come out, though, notice here's the bottom. There's nothing down here. Everything that comes out of this has to be greater than or equal to 0 for y values, and then it goes up from there. Now this is the example of two linear functions. This one is this is the next one in your notes, and it behaves differently starting at 3 and negative 3. So here are my intervals. So in my first case, when I make my chart, x is in, x minus 1, but this is going to be x is less than or equal to 3. So I'm going to put negative 1 in here. Negative 1 minus negative 1 is negative 2. I might put 0 in here. 0 minus 1 is minus 1. But I'm going to go up to and test several values up to 3, because now my rule is going to change. Because now, if x's are greater than 3, I'm going to get 1 out. So this is x is greater than 3. So if I put 4 in, 1 comes out. If I put 6 in, 1 comes out. 7 in, 1 comes out. And so when I go to graph this, I have negative 1, negative 2. I have 0, negative 1. I have 2, 1. And I have 3, 2. Closed circle, so my graph goes that way. But at greater than 3, for whatever I put in, I get 1 out. And so this is constant. And so up to but not including 3 this way, I get a constant graph. These are extra ones that are not in your notes. I will come back to these at the end if I have time. Determine whether the graph represents a step function, a constant function, an absolute value function, or a piecewise function. Now, step functions are going to look like steps, or they're going to be open and go down. Okay, constant functions are going to look like that. Absolute values are V, and piecewise can be anything. They could have that up to a point, and then they could do something like this at that point, or they could be constant. They're going to have intervals where they behave differently. So obviously this one is constant, and this is an absolute value, simply by the shape of the graph. Now I'm going to go back to one of those extra examples, and you do have room at the bottom of your notes. I'm going to do this first one where my intervals change between -2. So my first graph at x and f of x, where that's x plus 2, is going to be for x's that are less than or equal to -2. So let's do -4. -4 plus 2 is -2. Let's do -3. -3 plus 2 is -1, and I'm going to include -2 because it's up to and including -2. So that piece of my graph graphs like this, where I have 1, 2, 3, 4, -2, 2, 3, -1, -2, 0. It obviously is going to continue, and this is a closed circle because it's up to and including. But then things change, and now when I do my x and my f of x, I'm going to get 3x out for x's that are greater than -2. So when I put -1 in here, I'm going to get -3. When I put -2 in, because I have to see what happens there, I get -6. When I put 0 in, I get 0 out. When I put 1 in, I get 3 out. So when I plot these, -1, 1, 2, -3. Now at -2, 1, 2, 3, 4, 5, 6. This is an open circle because it was up to but not including. At 0, 0, and at 1, 3, you can see I have a very steep upward growth in the blue, but slower downward growth in the green. So those are some examples of piecewise, step functions, and absolute value and constant functions. Good luck with your homework.